the Bay Area are interested in launching a platform of CubeSat satellites, 10 centimeter by 10 centimeter by 10 centimeter, putting a constellation up around the Earth of these, and then photographing the surface every day. So it's a tremendous undertaking, both from a sensing perspective and also from a communications perspective, to get all that data back down to Earth. And so since the satellite project is always whipped from the headlines of today's technology periodicals that dozens of people read across the planet, we are going to do something related to that effort. And so this is a common third architecture. The CubeSat usually just tumbles in space, so you use something that's not particularly directional to communications, something that's relatively omnidirectional, which we're going to learn really hampers your link budget. But if you're in low Earth orbit and you've got enough signal processing and you're not taking up too much bandwidth, you can do communications with that. Just blast it out everywhere and hope planet Earth is in one direction. That's the philosophy of the CubeSat. CubeSat satellites are often called picosatellites. And represents sort of third form factor that you'll see spacecraft take nowadays. Any questions so far? Yeah. Cell phone. Yeah, you usually put at least a few solar cells on every facet of this thing to make sure that you get some sort of pickup since you don't have any real attitude control. Some people are trying to put little momentum wheels on here, but usually the space mission is not super sophisticated. You're usually trying to measure one thing with the CubeSat or do one basic task of communications. So the power demands aren't that high. You can get away with just a couple of solar cells plastered over the device. You could, as long as it's within 10 centimeters, you could come up with a more sophisticated CubeSat that would unfurl a solar panel in space, or unfurl a dish antenna to go back to Earth. There's some people that are looking at inflatable dishes or unfurlable dishes like that for CubeSats in space to be up to communications. But as we're going to learn in about a month, you can exchange a non-zero amount of power between two points in space. You can also exchange a non-zero amount of information. So you won't be streaming video on your CubeSat, but you won't be able to do sufficient data even if the antenna is just a totally omnidirectional thing that can't point. So we'll do some analysis to show that'd be a fun workout problem in class. Okay, any other questions? Good question. Yeah. Yeah, so the CubeSat. Often the CubeSat is not a solid box. I should bring some good pictures in. I don't know if you want to look at the airspace. Do you know anybody working on CubeSats right now? So you get the bigger footage at you. You can do another button again, by the way. So, yeah, there's really a frame. You can bring in some pictures. We should show and tell us something. That'd be fun. But a lot of times your CubeSat, it doesn't fit in a 10 centimeter cube, but it doesn't necessarily have to be solid. So a lot of times it's just a frame and then the inner electronics are here. Which means you can put an antenna in a gap there so it's not influenced by the metal nearby. Because we'll learn it's a terrible thing for antennas to have to radiate in the presence of other metal. Some people even talk about using the superstructure itself as the antenna, designing it in such a way that it will actually radiate. That's all the frequency and some other issues that we'll get into. Good question. Any other questions? What is your CubeSat mission doing? Are you Liberty's account? Yes, it's a camera. Oh, okay. Trying to track out one of the three, I think. CubeSat that might work on the three. Even though ultimately they're probably contributing more to that problem. No, they're not. This is good. Okay, well, if there aren't any other questions about attitude control and launch systems, let's talk briefly about some of the options that are available to an engineer. In terms of power systems, we're electrical engineers and we often take it for granted, but we can't in space. This is one of the most daunting aspects of doing business in space is that you can't plug in the satellite. The satellite literally has to live forever in space during its entire usable lifetime, and it must take all of its power, or at least its power conversion hardware with it. And so there are generally four classes of power systems that you choose for your spacecraft. The first one, batteries. In a way, all the spacecraft have to have some sort of battery backup on board, something rechargeable that you can recharge, top off, and then use if something should happen to your spacecraft unexpected, or at least something that happens infrequent enough for you to actually plan around. For example, let's say you've got your three-axis stabilized satellite, and for one reason or another, it gets misaligned and the solar cells no longer point towards the sun. Well, then you just lost power. Or if it passes by the shadow of the Earth. Maybe it's in geostationary Earth orbit, you think, well, that's far enough away because everything's not aligned. As we learned earlier, you don't even really have to worry about passing through the shadow of the Earth, except for maybe once in a blue moon. And if you lose power, it's just a chicken and an egg problem, right? How are you going to have enough power to wake back up and orient your solar cells properly so that you get the power to continue operation? And so batteries are, in some form or another, are a necessity in spacecraft operation. They have a short lifetime, limited power output. You can't drive really heavy loads don't think about is basically that battery chemistry is heavily temperature dependent. And so the battery is usually encased with some sort of thermal and radiation protection so that it's not exposed directly to the sun. However, if you're in the shadow of space, the temperature plummets and you're well below freezing. So what you can relate the battery. Well, today was like Minnesota or really northern states. You have to plug in your car before you actually turn it on. You have to keep the engine locked in the battery before you turn it. Does anybody know what I'm talking about? You're from in Alaska? Yeah. They had to plug in the other one before the rest of the they just weren't using it the way they do, right? And so, because of that, and again, now you have this chicken and egg problem. You said, well, I just add a thermal warmer to my battery to make sure it operates in space. Well, wait a second, how do you drive it? You drive from the battery, you drive from the solar cell. Where do you get in the shadow? And you lose power for a few minutes. So you shut your battery and it cools off, you can't run the heater. And so what they typically do is they make these hockey puck type warmers that you put in with your battery. It contains some heavily encapsulated radioactive material to heat the batteries. There's this material that has a half-life, I don't know, 10 years or so, and it will slowly stay warm at a reasonable temperature well over the lifetime of the battery that you designed. And so at some point when the radioactive material runs out, you no longer maintain that acceptable temperature. You design it to a certain place so that all the other subsystems are also failing at the same time. It's not like running at least fuel. Solar cells are dying, and all the other spacecraft elements that are trying to put it there are falling apart as well. So that's a lesson to you. Never mind using satellite. It's worse than a car. Okay. So that's the batteries. Now, of course, the reason you want to use solar cells because the sun shines 11 times more intensely, or there's 11 times more harvestable power in space than there is on a bright sunny atmosphere on the surface of the Earth. And the sun never sets in space. So aside from a little bit of shadowing around a planet or something like that, you don't have to worry about the sun. So this limitless, ridiculous amount of energy is available to you. And this is a hand-in-glove fit that makes it work here in terms of how to get your power. It's like all of these solar cells to operate in space. The caveat there is that for Earth and satellites is fine. You do have to watch out when you start looking at deep space missions. Once you get past, say, Jupiter, there's not enough solar density to drive all the power transfer and communications. And so these are not useful in deep space. In fact, it used to be you could make solar cells past Mars, but we've gotten so good at making high-efficient, long-spectrum solar cells that you can now use them in Jupiter. I think you have coming to Galileo mission actually using solar cells in Jupiter. Which 20 years ago, we would have laughed at that idea. The efficiency just weren't there. But now we can do it. I remember we got some solar cell missions to Saturn here. But we'll see. Relatively high energy output. And of course, that's a design trade-off in your spacecraft. I can actually make as much energy as I want. Large lot of research that goes into making these high efficiency solar cells. High efficiency butter coming in. Politically dangerous. Because sometimes they are environmentally dangerous. it should happen to the spacecraft. And remember that's very common. You read about rockets blowing up all the time. What they do is a high-profile disaster. You do an unmanned spacecraft, but still every so often it happens. Why? Because rockets are bombs with holes in them. And you're taking a bunch of radioactive material and you're putting it on the top of a bomb with a hole in it. So people don't like the idea of that, especially when you're not launching anywhere in the vicinity of where you live. And so, generally, this technology, even though it's wonderfully bulletproof, even though a lot of engineering goes into encapsulating RTGs and making sure that they don't disperse radioactive material, even if there is a launch failure, they're only used for deep space missions or some mission or spacecraft that would require an unusual power demand that was long-lasting or higher power than what you could get with solar cells. So, those are your options. Do you have any questions so far? Yeah. Yeah, so that's a good question. The question was, what is used to shield electronics? So all spacecraft electronics have a thin sheet of aluminum shielding around them. That gets rid of a lot of the really heavy lumbering radiation like alpha particles and things like that. And then they don't typically get lead because A, it's too heavy, and B, there's only so much shielding that you can put around a piece of electronics. You can make it thick, really thick, and at the end of the day, you will only exclude a certain type of radiation. So really high energy cosmic rays, they're getting through no matter what you put around it. And so, the trade-off is to just put some aluminum casing around your electronics. That'll get rid of the really bad stuff. The other stuff you're going to have to live with anyway, and that's the current philosophy. And then there are a lot of other aspects to space certification of electronics. Even after you shield it, because there's something you just can't shield against, a lot of people will make their devices in triplicate so that in case one of them fails during a digital operation, so boom, you take the best of the three that are coming out. The best two of three, so to speak. So an example of actually how you alter the design of the hardware itself to withstand that sort of environment. And then there are some exotic materials that you can make transistors and electronics out of. You can use packages in some cases if you're desperate. But some space certification of electronics, I'll make a nice course in and of itself. It would be kind of neat. There are a lot of interesting places that you can actually test the electronics, a lot of laboratories that try to reproduce on Earth the radiation conditions that you would experience in space to see how your electronics would actually perform. And it's difficult to send your spacecraft before it goes up on the launch vehicle to one of these laboratories to certify its operation under those conditions. That's an important step in launching your spacecraft. Any other questions? Good questions. Okay, now we get into the meat of the course. We do one last subsystem, which will introduce us to the communications and the electronics that we'll be spending most of the course talking about. That is the RF subsystems, radio frequency subsystems. So it's a good chance for me to introduce, at least at a block diagram level, some of the terminologies that we're going to be using in satellite communications to discuss systems with the rest of the class. So what I'm going to do is sketch out a typical arrangement for a bit type transponder. What is a transponder? A transponder is a device that receives and then retransmits, and I can't think whatever it receives. What I'll put up here is an example of an analog transponder. One of the mainstays of satellite communications 20 or 30 years ago. Most systems have migrated towards digital, but we'll still need to understand the basic analog aspects of a satellite subsystem to understand the limits and engineering choices that face an engineer is doing a digital system. And I'll introduce you to all the block diagram terminologies that I'll be using in class. And the concept of spectral analysis too, which you can never review that stuff too much, right? And so a bit type transponder in satellite communications does exactly what the name suggests. I think they named it after the Bugs Bunny cartoons. You ever seen those Bugs Bunny? Like the hunter would be after him with a shotgun, shoot the gun, and the shot would come out. And Bugs Bunny would take a pipe and take a pin, and use it, and the shot would go in, and then come out that side and go back to the hunter. That's exactly what this thing does. It takes a signal from Earth, it turns it right back down to Earth. However, you got to change frequencies, and you got to clean up the signal a little bit, at least amplify it, so you have enough signal to noise ratio back to receive what was transmitted. So, what are the components of a bit type transponder?